Hello everybody. In the last class we were discussing about the induction motor, and then we had concluded with the manner in which the active power flows through the machine. We saw that the active power which enters the machine through the stator, and then there's some portion of the power that gets lost in the stator as I square R loss due to the winding resistance, and then it goes to the magnetic domain, and the magnetic domain you have the core losses due to hysteresis and eddy currents like in a transformer, and the remaining power goes into the rotor as the effective rotor power. And in the rotor again there are rotor conductors. There will be I square losses in the rotor conductors, and minusing that I square R losses, the remaining power goes to the mechanical shaft, and the mechanical shaft, if there is bearing frictions associated, some portion of that power goes it, and ultimately you will have the shaft power. So let us work out an example to get an idea of the power flow in the induction motor. So let us take a three-phase induction motor. Let me take an example from the book. So we have a three-phase induction motor. It has a synchronous speed ns as 1200 rpm, and it draws 80 kilowatts from the source, from the three-phase source. The copper loss plus the core loss or the iron loss in the stator amounts to 5 kilowatts. So if the motor runs at 1152 rpm, revolutions per minute, then let us try to find the power flow for such a motor. So let us first make a calculation. Let us have this so that we have an idea of what we are doing. Copy. Okay. So we have the stator, and to the stator there is an input power PS, and there is some loss PLS I square R loss. There is also some loss. This is the iron losses PI in the stator, and the remaining power goes to the rotor, which is PR. Now in the rotor there is some loss due to the finite resistance of the rotor conductors. So I square R loss there. The remaining power goes as the mechanical power which is developed. And in the bearings you can have some friction losses, and there is some loss which goes off as friction. So we will say P friction, and the remaining power goes as the shaft power, P shaft. Now, and we also know here that if we take this portion here, the rotor portion, PLR is equal to PR minus PM, and we saw that PR is nothing but torque into omega S minus PM torque into omega M. So it is nothing but T omega S, you take out common, and you have 1 minus omega M by omega S, and that is equal to slip times PR. So therefore PLR, the loss in the rotor is dependent on the slip, and therefore we can replace that by S times PR. So this is how the power flow occurs. Now let us calculate the various powers that will come here. Now if you look at the input, what is the input for this 3-phase induction motor which has a synchronous speed of 1200 RPM? The input is 80 kilowatts. Okay. So we have 80 kilowatts as the input. Now out of this, copper loss per plus core loss in the stator is 5 kilowatts. So this together is 5 kilowatts. So therefore PR, which is equal to PS minus PLS minus PI, which is equal to 80 minus 5, which is equal to 75 kilowatts. So this is 75 kilowatts. Now what is S? The slip S is given by NS minus NM by NS, which is equal to 1200 RPM minus 1152 RPM, which is the motor speed. Look at these two parts of the spec, by 1200, and that is equal to 0.04. So now what is SPR? SPR is equal to 0.04 into 75, which is equal to 4 into 7.5, which is 3 kilowatts. So this is 3 kilowatts. So this 3 kilowatts, what goes to the power as the mechanical power will be 72 kilowatts. Now let us say that the friction loss which is given by, let us say, like I square R, it is omega square into B, and we know omega square, which is 1152 RPM into radians, which is 2 pi by 60 is equal to 2 kilowatts. Let us say. So which means 2 kilowatts goes off here. So what is available at the shaft is 70 kilowatts. Is 70 kilowatts. Now let's say the efficiency. Efficiency is given by the power that is available at the shaft that can be delivered to the load P shaft by the power that is input at the stator PS, which is 70 by 80, which is 7 by 8. This is the efficiency of this particular motor. It's close to something like 88% efficiency, which is equal to 87.5%. Let me put it this way. This is equal to 0.875, and in terms of percentage, if you multiply it by 100, so you will get efficiency equal to 87.5%. Now let us see what is the torque. See, the torque that is generated by the rotor can be found out by the power. See, PR is the power that goes into the rotor, and there is of course some amount of power that goes off due to the I square R losses. So what is the mechanical power is PM. Now PM is 1 minus S into PR, PR minus SPR. PR minus SPR, that is 72 kilowatts. Now that is equal to torque that is generated by the motor, let me call that one as TG, into omega M. Or on the other hand, if we want to find the torque which is independent of omega M, you could use this equation also. But anyway, we have this, and therefore TG is equal to PM by omega M. TG is also equal to PR by omega S, or equal to PR by omega S if it is a synchronous frequency that you want to. Now we know the speeds, of course, in RPM. So to convert it into radians per second, what do? To convert it to radians per second, we have TG, which is equal to PM divided by omega M, which is equal to PM divided by NM in RPM. To convert it into radians per second, we have into 60 by 2 pi. So in this case, we have PM as 72, NM as 1152 into 60 by 2 pi. So this is the generated torque, the mechanical at the mechanical shaft. So now let us look at one important aspect of the induction motor, and that is the equivalent circuit. How do we represent the induction motor? Induction motor as an equivalent circuit. An equivalent circuit. You see that the operation of the induction motor is very similar to that of a three-phase transformer. So therefore, the equivalent circuit of the three-phase induction motor will be very similar to that of the three-phase transformer. Let us also consider that because of the symmetry in the induction motor, that is, all the three phases are balanced, you could consider the single phase equivalent circuit, per phase equivalent circuit of the induction motor, because it is the equivalent circuit is going to be duplicate for every other phase. So if we take the equivalent circuit of a transformer, we have, let us say we start with the primary terminals. Okay. Now starting from the primary terminals, we have an R primary, and here it would be, I will call it as R1, so that we keep it general between the transformer and the motor. And then we have an X sigma 1, the primary side leakage. We have the magnetizing reactance, and RC, which is the core loss component. Now this is followed by an ideal transformer which has some ratio 1:n, which has a ratio 1:n dot polarities. Okay. And on the secondary side, you have the leakage reactance X sigma 2 and the R2, which is the winding resistance of the secondary side, and this gets connected to the load. But we are just indicating up to the terminals, so let us say we take only up to the terminals. External circuits need not come into the picture. So this is the way the transformer is having the equivalent circuit. The same equivalent circuit of the transformer can also be applied to the induction motor. So let us go step by step to achieve the equivalent circuit of the transformer, starting from the standstill condition. So under standstill condition, what happens is there is no motion of the shaft, which means there is no power delivered to the shaft. The frequency of the rotor Fr is S times the frequency of the stator. So under standstill, S is equal to 1. So as S is equal to 1, the frequency of the rotor is also the same as that of the stator. Let us further make this ratio 1:1. We will make this 1:1. And let us short the rotor. The rotor is now shorted because in the case of the induction motor, the rotor is shorted, or in the case of the wound rotor induction motor, you could probably add a resistance there, and then that resistance could gradually be cut out. So effectively we have the resistance externally put, or a short plus R2, which is the winding resistance. Now all these things are put together in this form, and this looks exactly like that of a transformer. So now here, if you look at the currents flowing in this, the frequency of the currents and the voltages here is the same as Fr is equal to Fs. Whatever the frequency, source frequency we are applying here. Now if the motor starts rotating, the motor starts rotating, you have Fr which is equal to SFS, meaning the frequency of all this portion of the circuit is S times Fs, which is different from the S is smaller, and therefore it is going to be lower than the frequency of this portion of the circuit. Now as this is 1:1, so whatever we have the back EMF here, which is, let us say we call it E1, we have E2 equal to E1. And the induced EMF onto the rotor side, E2 is equal to E1 if it had been standstill, but would be equal to S times E1 because of the rotation that we saw earlier. So this is S times E1. Now because the frequency is SFS, the reactance here also will change. What was the reactance? Is J 2 pi Fs into L sigma 2. This was equal to J x sigma 2 during standstill. So as it starts rotating, the frequency is changing, and therefore it is no longer SFS, it is Fr, which is no longer Fs, but it is Fr, which is SFS. So there is one more term which gets added here, and that is S, and that is S into standstill reactance. So what gets changed is the reactance J S x sigma 2. Of course all these are also J. R2, the resistance is not dependent on the frequency, so they are not going to get changed. Okay. So these are the changes that occur when the motor is in motion, which is, one is the induced EMF is S times E1, the frequency is SFS, because of that the reactance is changed, and that is this. Okay. Now this is the actual equivalent circuit of the induction motor, but we could make a slight approximation, that is, for high power motors, this current, the current which is going to flow through the magnetizing portion I0 that we used to call, is going to be a smaller fraction of the total load current, and therefore this can be shifted on this side, that is, this portion can be shifted to this portion. The errors will be a very small insignificant fraction without loss of generality, but it will make the analysis much more easier. Therefore we call this one as R, sorry, this is JXM, and this is RC, the core loss component. So this would be the modified equivalent circuit for higher powers, that is, for powers greater than, let us say, 2 to 3 kilowatts. This can be safely used without much error. But if it is fractional horsepower motors, then we have to use the one which is the more accurate model, which means that the magnetizing component will come there in between. Okay. Now we have the situation. Let us copy this figure and take it to the next page so that we have now more space. Yeah. Now let us see the current. Now if we take the current which is flowing here, let's say this is I1, it is the same current that is also flowing here, which is I2. I2 and I1 will be the same. Effective values will be the same, because this is the effective values that I am talking of, because of the 1:1 turns ratio. So even if the frequencies are different, the effective values are the same. So as a result, I1 is equal to I2, and let us look at this portion of the circuit. So I1, I2 is given by SE1, that is the source, divided by the impedance, which is R2 plus JSX sigma 2. JSX sigma 2, and this is equal to E1 by R2 by S plus JX sigma 2. This is equal to E1 by Z. Now this is the Z2 as seen from this side, because Z2 is E1 by I1. So E1 by I1 is here. So therefore, as seen from here, Z2 is this, which is equal to R2 by S plus JX sigma 2. So let us shift everything onto this side, so that we can eliminate the transformer portion. So which means we have now reactance, magnetizing reactance, core loss component. This is followed by R1, and that is followed by Jx sigma 1, the primary side. Now here let us put Z2, which is Jx sigma 2 plus R2 by S, and then you have the ideal transformer, and as it is shifted onto this side, there is of course a short here, and this is open. So it is as good as that 1:1 transformer not being there, so we can effectively remove all these things. We have it like that. So this becomes the effective equivalent circuit of the induction motor now, and to this we add the following things. Let me slightly modify this in placing. Let me make it like that, so that you will see this type in the textbooks, R2 by S. So you will see that the S is figuring in the rotor, effective rotor resistance. So this is like the effective load. At standstill, R2 is, so if I say the load, this is the effective load. Effective load at standstill, S is equal to 1, the load resistor is equal to R2. As S increases, you will see that, sorry, as S decreases, you will see that this portion starts increasing, and for the same current that will flow, you have more power which comes into effect, that is I square R. But if you look at the actual operation, you will see that in the induction motor characteristic we have something like that, isn't it? This is the torque, and let me say that this is the speed, shaft speed, and we are here. So this is the operating point that we are going to be most of the time. This is NS. This is where slip is equal to 0. This is at slip at maximum torque. Slip at, or we will call it as SM, slip at maximum torque. So this is the range of variation of slip, because the operating point can be somewhere here or here or here or here along this. So when S is 0, it is infinite. the resistance is infinite. That is, at S equal to 0, load resistor is infinite, which means at this point there is no power transfer to the load like open circuit. Now as S starts decreasing, here increasing, this is S is equal to 1. So as S starts increasing somewhere here, the effective load resistor starts coming down. So the load resistor which is equal to R2 by S. So as S starts increasing, the effective load resistor starts coming down, and therefore it can draw more current, and I square R that goes to the load. So we have the final equivalent circuit is like this. We have XM, we have JXM. I will write all those things later. We have R1, and this. So this is the equivalent circuit of the induction motor. This is JXM, this is RC, this is R1, the stator resistance, this is JX sigma 1, standstill stator leakage reactance, stator side leakage reactance, rotor side leakage reactance, and this is R2 rotor, effective rotor resistance, which is dependent on the slip. And we connect the source effective value, let's say this is EG, which is from the generator. It is connected like that. So this current is the stator current, and we call that one as IS. And out of this IS, the stator current, some portion goes for the magnetizing component I naught. So in I naught we have IM, IC, and in this you have I1 which flows through. So I1 is what is flowing through this equivalent major part of the equivalent circuit, which is the stator and the rotor equivalent brought on towards the primary side. Now let us draw the vector diagram for this with respect to, let us say, EG. Let us have this axis. Now let's say EG is my reference. We will draw EG. This is EG. So we start with the phasor EG. Now lagging EG is all the currents, because they are all inductive in reactance. And this IS is also going to lag EG. So let us say this is IS. Now Is is the sum of I0 plus I1. Now if you take I0 to compute I0, the drop IC is going to be in phase with Eg. So we have IC and we have IM, and that is going to give you I0. Resultant of that is I0. Now I0 and I1, if you look at the voltage at this potential is I1, and I1 is going to lag Eg, but we have here Is. So Is minus I0 is I1. So Is minus I0, let me draw this a bit clearly. In black. So we have this Is. We take parallel of I0 minus I0 minus I0 will be I1. So that is I1. So this is how the vector diagram would look like in the case of the induction motor. Let us have this diagram, that is the equivalent circuit. Let me copy that, paste. Let us see how the let us list down the power flow equations. Okay. What is the active power absorbed by the motor? The active power absorbed by the motor. So the active power absorbed by the motor is Eg square by Rm Rc, that is the core loss component, plus I1 square R1, that is the loss in this resistance, plus I1 square R2 by S, that is the one which goes to the load. So this is the active power absorbed by the motor. We will call this one, let us say, P. And the reactive power absorbed by the motor. So the reactive power absorbed by the motor, we will call that one as Q, is the one stored in JXM. So this is Eg square by Xm, magnetizing. In the leakages, X sigma 1 and X sigma 2, the leakage reactances, plus I1 square X sigma 1 plus X sigma 2. So this is the reactive power which is absorbed by the motor. Paste. Let us shift this. Okay. Yeah. Then third, the apparent power. The apparent power absorbed by motor is, that is the VA, is given by square root of P square, that is the active power, plus Q square. Then fourth, what is the power factor? Power factor. Now the power factor of the motor is actually as seen at the stator, here. Now we have the active and the reactive power, and therefore we know that this is the active power, orthogonal is the reactive power, and then this is the VA. This is the power factor angle. So VA cos theta should be equal to P. So power factor PF is equal to cos theta is equal to P by VA. Then what else can we obtain from the circuit? Then we have the line current, the line current I stator is, now we know the voltage, we know the apparent power. So from the apparent power and the voltage, we know the apparent power VA divided by EG will be the effective value of the stator current. This is also called the stator current. So let us have also the active power supplied to rotor. So what gets supplied to the rotor? The power that enters, the active power that enters the stator minus the stator I square R loss to the stator resistance minus the core loss that is due to RC. So active power supplied to the rotor, which is PR, is nothing but the active power of the input P minus IC square RC minus I1 square R1, or we could just take this portion of the circuit, it is also I1 square R2 by S. I1 square R2 by S, isn't it? If we look at the active power here, you see that this is the core loss component, this is the stator winding resistance loss component, and this is the PR which goes to the rotor, and this is the portion which is the active power that is supplied to the rotor, and that is that. Next, paste. So we have point 7 here now. The power dissipated in the rotor. power lost in the rotor conductors is power lost is given by slip times PR. PLR actually will be basically I1 square R2, which is nothing but slip times PR, isn't it? If we look at slip times PR, which is equal to slip times I1 square R2 by S, which is equal to I1 square R2. This is the power lost in the rotor. Then we have to find out the mechanical power PM. The mechanical power developed by the motor. The mechanical power developed by the motor PM is PR minus what is lost in the rotor, and that is nothing but this. So you have I1 square R2 by S minus I1 square R2, which is I1 square R2 1 by S minus 1, which is equal to I1 square R2 1 minus S by S. Which is equal to PR 1 minus S. Then we have point 9. The torque developed by the motor. So T, which is equal to PM into PM by Nm into 60 by 2 pi, which is equal to 60 by 2 pi PM is PR into 1 minus S and Nm is Ns into 1 minus S. So you can so say 60 by 2 pi PR by Ns. So either you can use this equation, if you know PM and Nm, or you can use this equation PR and Ns. Then of course the last point let us put down, that is the efficiency. So efficiency is given by P shaft, that is if you minus the friction. So PM minus P friction by the P, in this case PS. So the total input power P, which is calculated. If friction is not known, then you can say PM by P. So all the information can be obtained also from the directly from the equivalent circuit of the motor. So we saw here that the induction motor is not actually a very complex system. It can be represented like a transformer. You have the equivalent circuit almost like a transformer, except two minor variations. In fact, under the standstill condition, it is just like the transformer. And in the case of the motor in motion, there is a slip. The load is R2 by S, which is a function of the slip. And the leakage reactances, when you take it into the equivalent stator side equivalence, they don't have a variation with respect to frequency because the stator frequency is constant. The variation in the speed is taken care of by the R2 by S component. Otherwise, the equivalent circuit is just the same as in the case of the transformer. We saw the phasor diagram, and also from the phasor diagram and from the equivalent circuit, we were able to also list down the various equations for the active power flow and the reactive power flow components of the induction motor. Now, if the slip was negative, we said that the induction motor becomes a generator. In the case of the induction motor acting as the generator, the equivalent circuit is still the same. The only difference is that the slip S is negative. So R2 by S becomes negative, which means the polarity is reversed, which means now that it is pumping energy back into the mains. So it will look like that because the slip becomes negative, this becomes a source. This portion would become a source in the case of induction generator. The polarity would reverse and then starts pumping energy back into the mains. So by reversal of polarity, it could be the reversal in the voltage polarity or reversal in the current, because it is now acting against I1, and then it will pump more current than I1, and therefore the current reverses, and therefore the power flow is from the mechanical side to the electrical side. So the same equivalent circuit can be used even for the induction generator. We will work out a very simple example of the induction generator in the next class, and then conclude the topic of the induction motor. Thank you for now.